So today is our last conversation before our little meeting of the minds on Thursday. I'm going to wait until I finish this presentation today, and I'm going to completely rewrite the exam tonight and tomorrow. I want to make sure that there's nothing that I haven't directly spoken to you about on the exam. And a big part of the exam, honestly, is comparing and contrasting the autonomic nervous system, not a big part, but I mean you need to understand how the autonomic nervous system works differently than the endocrine system. I had a couple of emails. Well, what do you mean? Well, you tell me. What does the autonomic nervous system do? It's nerves, right? Neurons. So how do neurons work? They send action potentials to neurotransmitters. That's a very specific thing, right? It's going to a cell. It's going to a muscle. It's going to cardiac muscle, to a gland, it's going directly to the effector, isn't it? And it uses chemicals called neurotransmitters to affect a change, okay? Versus the endocrine system, which is all based upon hormones being released into the general circulation and traveling everywhere and only affecting those cells which are at the moment expressing the receptor for that particular hormone. So that's a big difference, right? They're both using chemicals. And then think about the timing of them. Neurotransmitters, we know that action potentials are quick, right? Those neurotransmitters are released and they have an effect for a very, very short time. And then those neurotransmitters, think of acetylcholine and acetylcholinesterase, are erased and allow the signal to be resent. But once a hormone is in the bloodstream, it's there, right? And it's going to be there for a while. So when the bear walks in the room and chases you, you know that your heart rate's up for a while. It doesn't just come right back down, which is very different from a neurotransmitter sending a signal to your finger, telling your finger to bend, and then it's back in a moment later. So think about those very general ideas, how neurotransmitters and the nervous system work differently than hormones. They both, if you think about the autonomic nervous system, it can be both a stimulatory or an inhibitory signal, right? And we see that hormones also can be either stimulatory or inhibitory. So that's another compare and contrast kind of idea, isn't it? So there was a question about that. I'm going to use Venn diagrams, I'm pretty sure, as I think about this. I'm going to use a Venn diagram. In fact, I did this in the 105 class. We had 105 with me. And I'll have a couple of Venn diagrams, meaning, I'll do it on here, meaning I will have a couple of circles, right? And one circle would be for the endocrine system, and one would be for the autonomic nervous system. And then I would give you some facts down here. Fact 1, fact 2, fact 3, fact 4. And if that fact only deals with the endocrine system, you'd put it over on this side, and I'd probably have that as A. And if it only deals with the autonomic nervous system, it would be B. And if it deals with both, I don't know if I'll either have you bubble in C on the test or I'd have you bubble in A and B both. I don't know which, right? And then if it does neither, doesn't involve either one, I might have it as a D and have it outside the circle. So just think about the different facts that I've discussed. And if I gave you a fact, does it apply just to one system or the other or to both? Right? And I would probably have a Venn diagram for endocrine versus autonomic. I probably have another one that would be sympathetic versus parasympathetic. Okay, and as you listen to that lecture that I presented on YouTube, just think about what happens when your body is chased by the bear, sympathetic, and what happens instead when you're resting, digesting by the campfire, roasting marshmallows. Okay, parasympathetic. And if you just kind of put those two things together, that whole talk on autonomic nervous system, honestly, I don't think I said much that I hadn't already described in the previous semester. So that shouldn't have been strangely out of place or oddly unfamiliar to you. I think just review that and you'll be in good shape. The test will be all we'll do on Thursday. I suspect similar in maybe not quite as many questions as last time. Again, I don't know, but I don't think time will be an issue. Time wasn't an issue last time. I don't, at this point, anticipate a short answer question. I'm thinking my short answer questions would have been what I'm putting into the Venn diagrams, And rather than having you write out what are the 5 differences or comparisons between the autonomic and the endocrine system, I will instead create the question as a Venn diagram and just have you use the bubble sheet. Okay, it's just more efficient on my time for sure, and I don't think most of you enjoy writing, so it'll be okay. If you know it, you'll be fine. Questions for me. So this test will be autonomic nervous system. That was chapter 14. Chapter 16, we spent 2 days talking about hormones. That'll be the most of it. It really will be most about the hormones. Know the organs, the glands that are making the hormones, know what tissues are responding to those hormones, and know the basic idea of what those hormones are doing. That's a reasonable large amount of information, a pretty large vat of information. And then today's talk, I think you'll find to be very reasonable, very comfortable. I'll be talking a little bit about fractures and bone, and then I'll be specifically talking about parathyroid hormone and calcitonin. And when you hear those 2 hormones, hopefully you're thinking, something about calcium. And the parathyroid and calcitonin story we'll tell a little bit more in detail today, and that'll certainly be a focus of you as we think about those 2 antagonistic hormones and how they deal with calcium regulation. I saw a hand or 2. Yes?
Can you explain just crin and
Sure.
autocrine and para?
Right, so as the word suggests, crin means what? If we don't know crin, we're going to have a long conversation, right? Crine or crin means to endocrine, to secrete hormones within the body, right, in the bloodstream. So what would paracrine mean? Para means next to. So in a paracrine situation, a cell is going to release a compound, a molecule of any kind. And it's not going to enter into the bloodstream and go far, far away like hormones do. It's simply going to contact the neighboring cells, the cells that are nearby. So a molecule that only interacts with nearby cells would be considered a paracrine relationship. Autocrine, auto means self. So an autocrine relationship, the hormone's released by a cell, and that very same cell responds to what it's making. It's like this positive feedback loop. It creates a molecule and responds to it itself. Auto means self. So it secretes and responds to its own signals. Okay, and what was the other one? Juxta, it means a lot like para. Okay, it's just nearby. Okay, you'll hear juxta or paracrine. They're typically, for the most part, they're kind of interchanged. I won't make a distinction between those 2. So juxta and paracrine, just kind of in the neighborhood, not getting into the bloodstream, not going systemic, not heading all over the body, just talking to the neighboring cells. Autocrine, talking to yourself. And endocrine, the whole body is going to see this hormone. And that's different than the nervous system. Again, the nervous system is very directed, right? The signal, the neurotransmitter, the action potential goes to a particular place. It releases the neurotransmitter. And now the effector muscle gland will respond to that neurotransmitter. Does that clarify those 2 or 3 terms? Okay. Anything else? Anything else? Okay, if you think about something, please interrupt me and let me know. Okay. Let's go back to chapter 6. Much of what I'm going to tell you builds upon what I think should be knowledge that you're carrying around in your back pocket. I will ask you to review, just kind of flip through the first few pages of Martini, remind yourself what an osteocyte is, remind yourself about compact bone versus spongy bone, remind yourself about the basic structures of bone. I won't quiz you directly on that content, but that information may, jiggle some ideas and help you make more sense of where I'm heading. I'm telling you to review module 6.1 to 6.8. However, I think I'm going to forward to about 6.7, and I'm going to pick up with 6.7. Let me just confirm that with you. So I'm just going to flip through. We're just talking about what is the skeletal system. This is clearly 105 stuff. Bones come in different shapes. We got all this. Bones have markings. Boy, we know a whole bunch of bone markings, and I'm not going to quiz you on bone markings. Remember that bones have a diaphysis, the shaft, and epiphysis, the knobby end of the long bone. So that's what this is all about. And then also it goes into the cells that make up bone. The cells that make the bone are the osteoblasts. And the osteoblasts, once they make the bone and cocoon themselves within the little lacunae, they go into semi-retirement, and they're now called osteocytes. Right? Osteocytes are found within the lacunae. Osteoblasts were the cells physically and actively building the bone. Then there were osteoclasts, and those cells were all busy doing what? Yeah, the osteoclasts were chewing it up, right? Clast, we know, means breakdown. So those are the cells that were chewing down the bone. And osteoclasts get a really bad rap because we know that when osteoclasts kind of go out of control, bone becomes demineralized or becomes more osteoporotic, and that's a concern. But we need to remember that throughout our lifetime, bone is the primary reservoir, it's the primary silo for storing calcium in our body. And we need calcium. We saw how important calcium was in action potentials. Right? If you didn't have enough calcium, and that action potential came down the axon terminus, if there wasn't calcium in the environment to come in and cause the neurotransmitters to exocytose, right, your nervous system would shut down. We're going to see when we get to the muscle. After this unit, we'll start talking about muscle and muscle physiology and muscle contraction. And we'll see there how critically important calcium is to muscle contraction. We'll also, when we get to blood in the heart, we'll talk about how important calcium is in the heart as well as in blood clotting. So we need calcium. We need it in a lot of certain times, but we can't have high calcium in our blood all the time. High calcium in your blood all the time can cause things like kidney stones. And you know, we want to be able to store this calcium in a place, and that's where the bones are. The bones are the storage place for the calcium. What's the other molecule, the other mineral besides calcium that's stored in our bones? Phosphorus or phosphates, right? And phosphates, when you think of phosphates, what two molecules hopefully come to mind? Why do we need to have phosphates stored and available all the time? A little molecule called ATP, right? Phosphorus, it's a phosphate molecule, pretty important for energy. And nucleic acids, DNA and RNA, that backbone of that molecule is a sugar-phosphate backbone. So clearly we need phosphate also in high concentrations. Again, we need these osteoclasts to break up the bone to release the calcium and the phosphate when needed. And we're going to be talking about what hormones regulate this process. And when there's plenty of calcium and phosphorus around, we want to build bone. And we're kind of in an equilibrium, we're in a nice homeostatic equilibrium throughout most of our life. You never want calcium and phosphate in your blood, both in high concentrations, because what do calcium and phosphate do when they get together? They lock together and they make little crystals, right? They easily make calcium phosphate molecules. And that's a problem. You don't want crystals floating around your blood. And you don't want, because if you have too many of these crystals, we call those kidney stones, right? If you get too much calcium, too much phosphate, if you're overdoing your supplements, and rather than taking the 1,200 or so milligrams a day that's recommended of calcium, and you think, let me take twice as much, grandma had osteoporosis. No, right? You don't want to be taking too much calcium because, again, too much can cause an imbalance and can lead to kidney stones. So I just kind of took that aside to remind you about osteoblasts and osteoclasts and how these cells are kind of doing this constant battle, releasing and storing calcium and phosphate in your blood and your bone. And the overall structure of the osteon and how bones grow bigger in diameter. And, oh, by the way, bones grow longer. We got this. But let me pick up right here with 6.7, okay? Just as a quick review. So 6.7, whatever page that is on, I left all these early slides in your pack so that you could just go back and review quickly these major ideas. So endochondral ossification. Ossification is the process of making bone. If something is ossified, it's becoming bone-like. And what does this word endochondral tell us about how most of your skeleton is produced? Endo, within, chondro, cartilage, right? So this suggests to us that your bone, most of it came from within a cartilage precursor, within a cartilage template. And where is that cartilage in a young person's bone? Right? Your bones are bone, except at the growth plate, right? What's in the growth plate? The growth plate is still chondroblasts that are still making cartilage. And as those cartilage cells are dividing, they're pushing and making the bones longer, right? And then what happens when we reach puberty? Yeah, we stop growing, right? Or at least the estrogen, right? Women stop growing pretty quickly. So the estrogen that's produced by the ovaries at puberty in women sort of tell those growth plates to hurry up and fuse. And so most women have reached their adult height within 18 or so months of menses. Whereas testosterone, which starts being produced in high amounts with puberty in males, that hormone tells the epiphyseal plates to get busy and to divide more. And so guys typically have a growth spurt with puberty that can continue into college. I mean, some guys will continue to grow a couple more inches into their early 20s. Okay, so that's the idea of endochondral ossification. It's starting as a cartilage model. And let me just remind you of this as we go through this. So the cartilage will get bigger. Remember that cartilage is avascular. You remember that? And this is hyaline cartilage. I didn't say that. This skeletal precursor is hyaline cartilage. This is that glassy, translucent type of cartilage. It's the only cartilage we saw in lab. It's the only one we reviewed in the histology section. It's the one with the little eyeballs looking back at you, right? Cartilage has little chondroblasts sitting in the lacunae. And what happens is that, and I've got a picture coming up, but you have this chunk of cartilage that's shaped basically like your bones. It's avascular. And blood vessels begin to permeate and knock on the outside door of those chunks of cartilage. And with that blood and with the oxygen that comes with the blood, those chondrocytes living in the lacunae are differentiated, become osteocytes. So the cartilage becomes bone-like when it encounters oxygen. Okay, so those blood vessels go in, and now the center of the bone, the shaft of the bone, the diaphysis, will become ossified. And we call this the primary ossification center because it's the first place it happens. It happens first in the shaft, in the diaphysis. Okay? And then the second place is that it also starts to happen, the blood vessels begin to permeate in from both of the epiphyses, so both the proximal and the distal end. And so now you've got bony ends, and you've got a bony center, but in the center at that growth plate, it's still going to maintain cartilage. That cartilage is still avascular, and you've got cartilage cells, chondrocytes and chondroblasts, that are dividing and lengthening the bone. Now, like I said, at puberty, with the onset of sex hormones, that growth plate will be fused down. And then what does one see? Do you see a gap anymore? Now you see instead a epiphyseal line. So this story is not hopefully unfamiliar to you. Let's just take a look at the pictures as I just described them. So we start off in the embryo, in the fetus. The skeleton is just a chunk of avascular cartilage. It resembles the shape of the bone, not quite as detailed, but it still has the general idea. If you look at a 3-month-old fetus, you will be able to shine a flashlight right through it. I mean, literally, it's translucent. The whole skeleton, it's very, very translucent. And again, at the beginning, right, these cells in here are what? These are still cartilage cells. So those are chondrocytes hanging out in the lacunae, little eyeballs looking at you. And at some point, blood vessels start permeating into the diaphysis, into the shaft. With the incoming blood and oxygen, these cells in the shaft become the osteocyte. They are differentiated into bone cells, and that's the primary place that it happens, in the shaft. But also, there's going to be infiltration into the two ends. So the epiphyses are also going to get blood flow. And those are going to be the secondary ossification centers because they happen second. And so now what do we have in a bone? We now have bone on the inside in the diaphysis, and we have bone at the two epiphyses. But there will maintain a growth plate at the end, so we're kind of going over to the end here, and also around the top of the bone, where there's going to be articulation with another bone, there would also be a continuation of that same cartilage, because around the edges of your bones, that's hyaline cartilage, as is the growth plate. So it's all hyaline cartilage. And then what happens with puberty is that that growth plate is closed down earlier with women and a little bit later with guys. And as that growth plate closes, we're left now with evidence where there used to be a gap, but it's now called the epiphyseal line. If you see the line, that bone has reached its adult length. It's not going to get any longer. If you still see a gap, then that bone is not yet completely elongated. And so a 12-year-old, you'd have a pretty good sized gap, 5 and 7 and 12 years old. And then a 15-year-old might have a little bit smaller gap, and an 18-year-old might be almost closed down if it's a guy. And eventually they would completely close down to the epiphyseal line. So what I just told you in words is now there in a picture as a reminder of how this whole thing works. Now there's stages of this whole thing, and here we go. So in the cartilaginous region, right, the blue area is the cartilage. Those are good old chondrocytes. They're hanging out in the lacunae. And here's the blood that's permeating up toward those chondrocytes. And again, as oxygen starts getting toward them, they start to degenerate, if you will, and turn into osteocytes. So it's not just oxygen that does this, but the blood brings with it other factors and other hormonal kind of signals that cause these cells to completely switch their identity to osteocytes. Okay. So as I mentioned, estrogen closes things down, and testosterone encourages the growth at male puberty. And at some point, that epiphyseal cartilage completely disappears to become the line. Any concern there in that story? Is that all reasonably familiar? Okay. Intramembranous ossification would be bone that comes, quote, from within a membrane. This is a limited part of your skeleton that did not first come from cartilage. The endochondral, the story I just told you, is how your long bones are made and your short bones are made. So pretty much everything in your appendicular skeleton, everything in your arms and legs is going to be made from a cartilaginous model through that endochondral form of ossification. Other bones in your body, though, are instead not going to start off with cartilage, but will actually start off with another type of precursor to bone. And this is essentially your flat bones of your skull. Think temporal, parietal bones. This is your mandible. This is the much of the clavicle. And your patella is also made this way. So I guess I just lied, didn't I? Patella is the exception. Okay, so the patella is in this list. Everything else in your long bones and in your appendicular skeleton is going to be made by endochondral. And basically, this is just a bone becomes bone. It's just a different way of developing. It's not going to start off with cartilage. So here, there would still be an ossification. This is still pre-bone becoming bone. And when you see this word mesenchymal, these are cells that are derived from the mesoderm. Remember the mesoderm? In the early embryo, the blastula, right, that smallest cells with a little bit of a hollow center, becomes a 3-layered ball called a gastrula. And at that stage, you set up 3 layers. There's the ectoderm on the outside of the embryo. There's the endoderm that makes up the tube-like centers of the embryo. And the mesoderm goes on to make the muscle and the connective tissues. So when you see the word mesenchyme, mes means middle. It's similar, essentially the same as the mesoderm. So the center of the embryo derives tissues that will begin to themselves secrete osteoid. When you see the word osteoid, what are osteoblasts making? What are they knitting together to make the bone? What are the components of bone? We've got calcium and phosphate. That'd be the mineral component. And what is the organic component? What's the primary protein in bone? What protein gives things strength? Collagen. Right? So your bones have a lot of collagen in them as a protein, as an organic molecule, and your osteoblasts are also pulling together the calcium and the phosphate. So when you see this word osteoid matrix, it's that making, the knitting together of the collagen with the calcium and phosphate crystals. Okay? So that becomes, quote, mineral. So that osteoid material, right, the calcium and phosphate and collagen becomes mineralized, and now we've got bone, right? We're forming a ossification center, and then the bones kind of grow out as little spicules, little pieces. And again, the osteocytes will get caught up inside these things, and we start making bone. Now, again, blood is going to enter these areas. Oxygen and blood are necessary to maintain the bone. And it's just going to keep going and keep going and keep going until basically you have made the flat bones and the other bones that I described. And you'll also get the spongy bone produced. So you get the same idea. You get the spongy bone and you get the compact bone. But it simply did not start with cartilage. That's really the big distinction I want to make here. I'm not going to ask you to draw out the step-by-step production of bone from intramembranous ossification. So we'll look at a picture of it. But basically, you've got these cells. They're not yet bone cells. They're these mesenchymal cells, or these cells that are derived from the mesoderm. And those cells themselves are going to start putting out this osteoid material, the calcium phosphate and the collagen. And then blood vessels will come in and will start making layers of bone, as well as make the spongy bone. When you're all done, man, that looks just like bone, right? Just ta-da, it happens. So we're not going to worry about that too much. This is a picture, basically histology, and you're looking at, in here, you got a lot of blood vessels traveling inside the bone, and you've got little osteocytes living in lacunae. That's not any different than what you've seen before. And out here, you have osteoblasts. These cells out here are osteoblasts, and what are they making? Osteoid, right? The bony-like material. And once they cocoon themselves in the osteoid, we would call them osteocytes, and that tissue would then look more like the more mature bone that you're used to seeing. This is all happening early. So this is happening at about week 8 of embryological development and continues through about week 10. By week 16, you can make out all the bones. Okay, so if you looked at about a 4-month-old skeleton fetus, you would be able to pretty much identify all of the bones of the body, just like you know them to be by that point. So again, if you had a flashlight and you were able to backlight an early fetus, you can literally see almost right through their bones. They're very, very translucent, and by the time we get to about 16 weeks, honestly, you could name every bone in this little guy. Okay? They're not all necessarily articulating, but you would see all the long bones and all the bones of the body. So I wanted to go back and just kind of review that. So what can go wrong? Let's talk about a few things that can go wrong during bone growth. There can be pituitary growth failure. Okay, so what hormone would you imagine is involved with growing? Growth hormone, right? Yeah, so if your pituitary, your anterior pituitary, is for some reason not making sufficient growth hormone, you might have some issues with bone development. So if you have inadequate growth hormone, then you would have abnormally short bones. Okay, you just would not have the bone lengthening that you would expect to see with normal hormone levels. We don't see this much. In fact, in this country, if a child walks into a pediatrics office and their parents are of relative normal height and their child is below the 5th percentile of height, they might consider giving them injections for growth hormone. It's not that uncommon. Now, if the parents are little, then clearly there's nothing wrong with their child. And there is a debate. There's an ethical debate about should parents be giving their kids growth hormone injections. I remember having a student years ago when I was teaching middle school, and he was a little bit shorter than most, but his parents weren't giants by any means. And you would expect that, most shorter boys are going to have a little growth spurt at some point. But the parents had been injecting this poor kid with growth hormone injections since he was at like 5. And I don't know. In the end, I'm not sure it made much of a difference. So that's one thing that can go wrong. That'd be more of an endocrine issue, right, where the growth hormone levels are not adequate. Then there's achondroplasia, right? There's TV shows on these folks now. There's a couple different things that can go wrong here. There can be a deficiency in some genes that are definitely involved with growth hormone or with growth factors that lengthen bones. And typically they're just, shorter, stockier limbs. Their trunk is of normal size, so their proportions are a little bit off, the achondroplasics, but everything else is totally normal, right? Their ability, their function, their ability to reproduce, everything else is absolutely normal. It's just that their long bones grow slowly. So the axial skeleton is really not that much affected. Again, it's the appendicular long bones that get mostly affected by achondroplasia. There are other problems called Marfan syndrome. This is also a genetic syndrome. And here, there's excessive cartilage formation. And these individuals are usually very tall, very lanky. They can stretch their arms and fingers in ways that would really seem abnormal. And there's evidence that perhaps even Abraham Lincoln had Marfans. It's not something that's going to affect your ability to function. You're going to be totally normal in all of the ways, but you're going to have unusually long, lanky limbs, and it also can affect vessels because with that can come some heart conditions and some other issues that sometimes are an issue. So you'll see some cardiovascular issues. I guess you could argue Lincoln didn't live long enough to find out that was going to be a problem, right? But you'll hear about Marfan syndrome sometimes, but just really lanky, can stretch their bones, hyperextend, things that are very different. Keep hitting the wrong button, sorry. So we've got achondroplasics, we've got Marfan syndrome, making extra cartilage, and then there is giantism. Now, if growth hormone is being overproduced since a young child, long before their epiphyseal plates have begun to close, then you can have giantism. So this would typically be a pituitary gland overproduction, typically a tumor, right? The pituitary gland is not easy to get to. It's not easy to do surgery there. And so if there's a pituitary tumor, it may be overproducing growth hormone, and that can lead to the giantism. Because the epiphyseal growth plates never seal, right? They just keep growing longer. There's no signal to say stop growing. Even the testosterone in this man couldn't have, or even if it was a woman, the estrogen wouldn't be enough to overcome the growth hormone overabundance, and they would just keep on growing. They typically have to try to remove the pituitary, which can be a real problem, irradiate it, do something to try to suppress it. They'll just keep on growing. And these folks usually die of cardiovascular issues. They're 7 foot plus tall. The heart really is not that good at pumping blood 7 feet. You don't see very many tall people in the nursing home, right? Tall people don't live as long as short people. It's just kind of a way it is because the cardiovascular system does take a greater work, right, to pump the blood further. So there's a little bit of a disadvantage in longevity with height. Not always, right? But overall, you'll see fewer tall people in the nursing home at older age than shorter people. And then what if that growth hormone problem, what if that pituitary gland is something that happens post-puberty? So the growth plates have already closed down, but now there's a pituitary tumor, and they're overproducing growth hormone. Now you get Shrek, right? You get Andre the Giant. This is acromegaly. Acro means extremity. Megaly means enlargement. So acromegaly is a overproduction of the growth hormones, and the bones get thicker. They don't get longer, right? We've already closed the growth plate, so we can't get longer, but the bones start getting thicker. So especially the jaw, especially the hands, but there's definitely some skeletal changes that occur. The bones are getting bigger around, and again, they'll just keep getting worse and worse and worse. But again, usually jaw, hands, face. You'll see a big thickening of the face. So just picture Shrek and what's his girlfriend's name again? Wife? Fiona, right? Question.
What happens when older folks start shrinking?
Well, there is, okay, so no doubt, I'm shorter than I used to be. So think about the cartilage, and I'll get to this a little bit, but in between all of your 24 vertebrae, right, there's a little piece of cartilage. And if that cartilage gets just a little bit thinner, so you got 24, if each of those shrinks by a millimeter, it's not very much, right? 24, right? You're going to start shrinking. You can easily shrink. What if each of those discs shrinks by, let's go with a tenth of a centimeter? Am I right? Doing my math in my head. But easily, you can easily shrink an inch, right? Just by shortening a little bit of each of the 24 discs. Now, what other structures change significantly with age? Not only the vertebra, but also the ligaments that hold the teeth in. So teeth get looser with age, right? And there are some other changes. And there's also, so the jaw, the teeth, the height overall definitely starts to have an effect. So just think about that little intravertebral disc shortening just a little bit between each of the vertebrae. Definitely some shortening. And then, what do we start getting bending over type issues? What do we call that? Right? Kyphosis, where the skeleton starts to change a little bit, and so they're bending over. That's also going to decrease their overall height. So those two things are the big ones. What else can go wrong? There's also a condition where the bones continue to deposit in weird places. This is a genetic mutation. It's very rare. Look at this. This is a person. You can definitely see there's some abnormal structure here, but this is their skeleton. And the skeleton just keeps depositing bone in all the wrong places. You could also call this ectopic, right? What's an ectopic pregnancy? One where the embryo is in the wrong place. This would be ectopic bone development. So things are happening in all the wrong places. And, there's no real treatment for this. And the lifespan is affected depending on the extent of it and when it all kicks in. You probably would never see a person with this condition, but again, what can go wrong? And then what else can go wrong? In utero, there can be club feet issues. This is more deal with boys. It's definitely more common in boys. It's still only a couple per thousand, and it can affect one or both feet. Part of it is thought to be constriction of the uterus and the feet not being able to extend normally. And so as a result, their feet club around, and there's some issues. This typically can be treated with casts or some surgery, typically, but the feet will usually just turn immediately, as you'll see here. Again, that's oftentimes, there can be a genetic component. All I know my mother said is that I had to wear special shoes for a couple of years. And so I had a little bit of that club foot issue. That's all I know. I don't know much more about it than that. But the feet turned out okay. And that's it for just what can go wrong. So it's all related, right? Most of it's related to hormones or to genetic mutations that affect the growth of bones. So just recognize achondroplasia, giantism versus acromegaly, and those are the big ones. So now let's really talk about the physiology of bone. We talked about how it grows and how it starts from cartilage, most of it. Let's get into really the minerals and the hormones that regulate this. And this is going to be the real big take-home lesson from today. We've already said this. What are bones made up of? They're a very important mineral reservoir for calcium and phosphate. Those are the two big ions or minerals that are stored in large amounts in your bones. And as I've said, calcium and phosphate are both critical to many of your physiological processes. What is bone made up of? 2/3 of bone is inorganic. When I say inorganic, non-organic, this is the calcium and phosphate stuff, right? So about 2/3 is calcium phosphate. The other 1/3 is organic, protein, collagen. Okay, so 2/3 calcium phosphate, 1/3 collagen. And 99% of your calcium at any one moment is stored up in these silos called bones. So what I've already just said in a figure, so 33%, the organic, another way of thinking about organic compounds are the macromolecules. And remember long ago, Chapter 2, 105, there were 4 groups of macromolecules: proteins, carbohydrates, lipids, and nucleic acids. So though 33% of your bone is pretty much organic, mostly collagen. And then we see that the inorganic component is the other 2/3, with calcium being a big one and phosphate being the other big one. There's some other things in there mixed in, but don't worry about that. But calcium and phosphate are the 2 big ones, okay? And so the bones store 99% of your calcium and a fair amount of your potassium, okay? Oh, sorry, I didn't mean to say potassium. I meant to say 99% of your phosphate. That's what I wanted to focus on. So most of your calcium, most of your phosphate, right, are stored in your bones. And those are the 2 I want you to be thinking about as we move forward. So calcium. It's the most abundant mineral in your body. And you've got 1 or 2 kilograms of it in your body. So there's a lot of it there. Again, 99% of it's bound up in your skeleton. And I've already told you that it's really important for muscles to contract and action potentials. We already appreciate that one. And it's important for blood to coagulate or to clot. You never want a really high concentration of it, again, because calcium in the wrong place at the wrong concentration can cause ectopic, right, out of place precipitation, and that can lead to cardiovascular problems. It can lead to atherosclerosis. It can lead to kidney stones and liver issues. So you never want this stuff to accumulate in the wrong place. So what we're going to be discovering here today is that the body spends a lot of energy making sure that calcium stays in that right concentration homeostatically. So what organs are involved with regulating your calcium? It makes sense that your digestive system's involved. Your gut is going to be absorbing calcium from your diet or not, depending upon some hormonal signals. So there'll be specific uptake or not uptake of calcium. Your bones, again, are taking up that calcium. Osteoblasts are going to use that extra calcium when it's available to build the bones. Osteoclasts are going to be called upon to release the calcium when there isn't enough available elsewhere. Your kidneys are also going to be a part of this regulation process because the kidneys are going to be controlling how much calcium is reabsorbed in the tubules and how much will be allowed to be released through excretion. So we'll see the kidneys are going to get involved with hormones, the gut's going to get involved with hormones, the bones are going to be talking with hormones here as well. So in order to keep your normal levels of calcium, right, we're going to be speaking to the gut, we're going to be talking about the balance with the bones, and we're going to be talking to the kidneys to maintain this. So we got 3 systems at least that are directly involved with maintaining calcium levels. So know the components of bone and what 3 systems are helping to regulate the calcium levels. What are the hormones that are doing this? What's influencing calcium? We've already introduced these hormones to you. They were part of the parade of endocrine glands. So we're going to spend a little bit more time talking about parathyroid hormone today and calcitonin. Parathyroid hormone made by the parathyroid gland, not difficult. Where are, I should say, the parathyroid glands? Para means next to thyroid, right? And they're actually on the back side. They're on the posterior side of the thyroid, parathyroid, next to the thyroid. And parathyroid hormone, right, it's going to be released from the parathyroid gland, go into the blood, endocrine, go to all tissues, and it's going to go to the bones, and it's going to tell the bones what? Well, first of all, when is it released? When is parathyroid released? When calcium is low, right? So when calcium is low, parathyroid will be released. And what's it going to do? It's going to go to the bones and say, hey, bones, let's go ahead and stimulate those osteoclasts. So what are they going to do? Pac-Man away, right? Starts chewing up some of the bone. As it chews up the bone, it's going to start releasing the calcium into the bloodstream. What do these osteoclasts release? Remember, what do osteoclasts release to help break down the bone? Am I hearing hydrochloric acid? Right? Good old, strong hydrochloric acid is being released from these cells. And what do we know? What does acid do to your bones? Breaks it down, right? That's why we don't want to be, you don't want to be swigging too much Coca-Cola in your mouth. It does erode your enamel. You don't want the bacteria in your mouth to build up a lot of acids because that acid breaks down enamel. It's why our Greek statues in our cemeteries, right, the monuments are getting faded because acid rain is eating away at the calcium limestone kind of statues. So again, we know acid eats away at minerals. Okay, so we know that. So the bones are going to upregulate their osteoclasts. The osteoclasts are going to start spitting out hydrochloric acid, and that's going to start resorbing bone. The word for breaking down bone is resorbing, right? Resorbing. If you're building up bone, we say that you're depositing. So deposition of bone would be the adding of bone to the skeleton. Resorption of bone is the removal or the breakdown or the demineralizing of the bone. So that PTH, that parathyroid hormone, is going to go to the bones. It's also going to go to the intestines. And there it's going to tell, right, it's being released because there's low calcium. So whatever calcium now comes in through the gut, comes in through the diet, you're now going to tell your gut to increase the absorption of calcium. So when you're having some yogurt, that calcium is going to be sucked up into your gut more easily as a result of parathyroid. And it's going to go to your kidneys, and this all makes sense. It's going to tell your kidneys what? Don't flush it, right? Reabsorb more calcium. That's going to happen in the tubules. And this is also putting another hormone into this. Parathyroid hormone will increase the release of another hormone called calcitriol. Now, calcitriol will also, again, stimulate calcium reabsorption. So we've got another little player here, calcitriol. It's another hormone. It's all involved with calcium, increasing calcium, and parathyroid turns on this hormone. So let's take a look at this picture. I love these diagrams. So if you had low calcium, right, low calcium, what does parathyroid hormone do? It goes to all of your body, and it affects the bones, telling them to do what? Release some calcium, get the osteoclasts chewing away, tells your gut to absorb more calcium, tells your kidneys not to release it. What do all these things do? Increase the calcium back to normal. Now, what is the antagonistic hormone to parathyroid hormone? There were at least two, strictly antagonistic hormone relationships that I shared with you last time. One was this one, parathyroid hormone with calcitonin. These two are antagonistic yin-yang. The other yin-yang pair that I told you about was insulin and glucagon, right? Those two also have this kind of opposing antagonistic relationship. So what would calcitonin be doing in this story? Calcitonin is going to be released when your calcium levels in the blood are too high. All right, they're too high. We got to get them down. Remember, we don't want high calcium. High calcium in the bones, high calcium in the blood can lead to problems. So we got to keep it under control. So calcitonin will be triggered. It'll be released from the thyroid gland. It's going to go throughout the body. Remember, it's made specifically by C cells. That's easy, right? C cells make calcitonin. They're the cells specifically in the thyroid that make this stuff. And what's it going to do? Well, it's going to go to the bones, and it's going to kind of shut down the osteoclasts. This all makes sense. I think it makes really good sense. It's going to tell the osteoclast to kind of cool it, and it's going to encourage calcium deposition to build up bone, tell the osteoblasts to kind of get busy. It's going to tell the gut, you know what, we don't really need as much calcium, so it's going to decrease the calcium absorption in the gut, and it's going to tell the kidneys, you know what, we don't need as much calcium, so let it go, let it flow. And again, that calcitriol would be inhibited. So we saw parathyroid upregulate calcitriol to get things back to normal. This calcitonin will decrease calcitriol and kind of do the opposite. Lovely little picture once again. High calcium levels. Thyroid gland will release calcitonin. It'll go to the bones and say, you know what? Don't chew away, but instead build. It'll go to the gut and say, we've got plenty right now, so please don't absorb it. Let it go through the feces. And the kidneys will be told, let it go. Collectively, all of these systems will bring about a decrease in the overall calcium. Every day, all the time, up and down, parathyroid, calcitonin. This is not something that happens during emergencies. This is happening daily, just like insulin and glucagon are constantly battling each other. A lot of energy. Imagine, your body is spending a lot of energy, a lot of effort to keep this stuff balanced, because think about all the critical processes that depend upon the proper levels of calcium, right? Without the nervous system, without muscles contracting, without blood clotting, that's called death, right? So we better keep this level, we better keep this well prepared, or keep this level well managed. Okay, so calcium, again, is being stored in the skeleton. We've talked about that. And what happens over time? If we're releasing too much calcium out of the bones, then the bones would naturally weaken. Right? So this is the problem. With time, with age, with disease, with imbalances, you can leach the bones of their calcium. Literally, this happens to pregnant women. I mean, if women are, during pregnancy, are not supplementing sufficiently, you've got a little skeleton being made inside you, and that little skeleton will win. And it will leach the calcium out of mama's bones to make its own, and mama's going to lose in the long run. So we got to be supplementing with calcium, make sure we're having plenty of calcium during pregnancy. And then the opposite, you're depositing calcium to make bones. We need that calcium around to do that. Again, too much calcium does not make an advantage. There's only so much calcium that can be put into your bones. And if you're consuming too much calcium, that extra calcium is floating in your blood. And now you've got kidney stones 5 years from now. So be careful on over-supplementing this stuff. And if you already eat 3 things of yogurt and a pound of cheese every day, don't take a vitamin. I mean, don't take a calcium supplement. You've already got plenty. Right? So make sure you're looking at your overall calcium intake on a daily basis, and look at the content, look at the label, and only supplement if you're not meeting that. But if you're already meeting that daily allowance, don't overdo it. It's just not worth it. Okay, so that's just a little bit about, again, how calcitonin and parathyroid hormone are working to keep your calcium levels at balance, and the bones need that balance in order to build and remodel properly. So let's talk a little bit about fracture. Again, this is not a brand new concept to you. Fractures, bones break. And as long as after the fracture, the bones are able to touch each other, bones will kind of naturally reattach and re-ossify and heal themselves, if you will. The problem is when the bones are broken and they touch each other, but they're not at the right angle, they will once again connect and ossify at a weird angle. right? And that can lead to a loss of function or strange skeletal changes. And we don't see it much in this country, right? Most people who get a broken bone are able to go to the emergency room and have that bone set in a cast, have pins put in, whatever it's taking, and we usually restore bone function pretty well after a fracture. But you go to other countries where they don't have that kind of care, and you'll see people with very abnormal fractures that have healed in a strange way because they didn't have that realignment done properly. So we know that bones break due to extreme mechanical stress. Collagen is strong. Calcium and phosphate are strong, but you can certainly break a bone. Who here has broken a bone? Anybody have that experience? So what happened? Anybody? Long bone?
That was my elbow.
Okay.
Thought I could fly when I was 3.
Thought you could fly, yep. I remember convincing my brother that Mary Poppins with an umbrella could pop off the garage roof, and convinced him that he should try that. So I think he suffered a couple fractures as a result of my suggestions. He was the little brother. I also found out that when you put dirt in one's mouth, it makes mud. That poor child. Anyway, but Big Brother took care of him well. So, but typically, right, bones typically heal well. A couple years ago, my then 10-year-old son was jumping on a trampoline with a neighbor boy, and oh, the poor kid snapped, right, his ulna and his radius. The parents are a little upset. I'm a little upset, but what do I know? The kid's 10. They're going to put a cast on it. It'll be fine, right? A little trauma, but everything's going to be fine. Nothing in the end is going to be negatively affected. So I wasn't too worried about that. When bones do break, we know that bones have a lot of vascular supply. So bones break, a lot of blood, and blood will be formed. There'll be a hematoma, like a big blood clot that will form where that broken bone occurred, and then repair will occur in basically 4 easy steps. So let's just go over those repair steps. Again, this is not, I remember going over this in 105. If you had me for 105, you've heard this in passing. So there'll be that fracture hematoma. Blood will be clotting as a result of the fracture, and that's going to be going on. There'll be some internal bleeding around that, but the blood will clot as long as there's no clotting disorders. And as a result, now macrophages will come along and start chewing up all the blood clot and all the fragments of the blood, and there'll be a callus formed. There'll be an internal callus and then an external callus. The internal callus is the spongy bone, right? So let's just think that this is a long bone. You've broken the diaphysis, and there's all that spongy bone in there. So first, the spongy bone will sort of reconnect, and then later, the outer layers will stabilize. That'll be the external callus. The first thing that will form, though, will be spongy bone. So spongy bone will first go in there. Now, during this time, this is why we need to have a cast on. We need to stabilize that bone and keep it from being moved too much during this time, because at this point, we're still basically going to go back to cartilage. The bone will kind of reform in the same way that it was formed in the first place. It'll go back to a cartilaginous kind of framework, and then move forward to being ossified. So it's the same kind of sequence. And again, some macrophages will go in there and chew away the old fragments and make way for the nice, new, clean ends. And then finally, you'll have some compact bone that will come along and replace the spongy bone. And over time, right, the bone is just as strong as it was. X-ray may show a little collar, a little bit around the outside edge. If you watch enough shows, they'll talk about how they'll look at an X-ray and they'll see that the child has clearly had fractures in the past, maybe as a sign of child abuse or some sort of trauma. And so you can see these for a while, but just to look at the pictures, we see that here the humerus has been broken, right? And in that area, there's a little hematoma, blood formation. And as long as those two parts of the bone can find each other again, and likely, again, in our society, we'd go to the doctor, they would realign those bones, they'd make sure that everything was put back together in close contact with each other. But again, on the outside, there'd be this cartilage that would start to form. So that blue area is cartilage, and that blue area will also be invaded with blood vessels, okay? And that, again, the cartilage will be differentiated into bone. And the first thing that will form will be spongy bone, and then eventually compact bone. So after fracture, there still may be along the outside edge of that bone evidence of a previous fracture. But as far as strength goes, it's usually going to be in really, really good shape. Now, what are some different classifications of fractures? Again, this is mostly review. I'll add a few more. If you hear about a closed fracture, that's one word you'll hear. You'll also hear about simple fractures. It's the same thing. Simple does not mean that the fix may be simple. Simple simply means that it didn't break through the skin. So a simple fracture is where it did not break through the skin. It's not a big bloody mess. You're only going to see, quote, the fracture in an x-ray. If instead it's a compound fracture, that tells us that it did break out through the skin. It doesn't mean that it's a more difficult break, right, as far as compound breaks. It's not like it's more pieces necessarily. It just means that it has broken through the skin and is more dramatic, right, to the parents and to the kid. Now, because it did break through the skin, it is a greater, it's a bigger mess. You've broken through the skin, you've got some infection issues, you've got some bleeding issues, but you may also just hear the word open for this. Transverse, all it means is that the bone was sliced right across, a transverse slice. There can be a spiral fracture. Spiral fractures are going to typically be made by someone who's in a rotating motion at the time of the fracture. So this could be a gymnast coming off. This could be a person who's doing a layup and they're kind of twisting, and as they come down, there's a spiral force, and you'll actually see the fracture lines in a spiral along that long bone. Unfortunately, though, spiral fractures are also evidence sometimes of child abuse. So the parents who grab their kids and twist their arm can cause a twisting fracture, and that can be if you get a twisting fracture and you haven't been jumping off a gymnastics mount or something, you're probably going to get the attention of a doctor and a CPS worker at the hospital, asking a few very uncomfortable questions about how did this accident happen? Tell me what was going on with the kid. They've got this spiral fracture. Especially if they have other ones, right? If the X-ray shows previous, problems, you're going to be in some trouble probably, right? Got a lot of explaining to do. And then displaced fracture. So this is going to be where you're going to a displaced fracture. What you want to do, a non-displaced fracture. Let me put it that way. A non-displaced fracture is going to retain normal alignment. If you have a displaced fracture, the bones are no longer in their normal anatomic position, and if they're not realigned by the doctor, then they could create abnormal bone as they reattach. There can be compression, a lot of stress, some sort of compression fracture, jumping off the roof, or being in an accident where maybe your leg is extended as a driver, and there's impact, and there's a compression fracture of the femur up into the os coccyx, something like that, a lot of force. Green stick fractures. A green stick, when I think of green stick, it's just not a stick that's going to snap, right? You go out and you're getting kindle for a fire, you want to find dried up bulb sticks that are going to snap. And if you go out and find a greener stick, when you snap it, it's not going to snap, it's just going to bend. So a green stick fracture is an incomplete fracture, and it didn't break all the way through. So you may hear it called an incomplete fracture. One side is broken, the other side, however, is kind of like bent. And this is going to be more common in younger kids where their bones are still not as, quote, ossified. So the bone won't have snapped quite as completely. There's still more of a cartilaginous component. Comminuted fracture simply means that there's been a shattering. And you don't just have the femur snapped in two, you've got many little pieces. Typically, the comminuted fracture, those little fragments may not just realign on their own, so there may have to be surgery to go in and get rid of some of those fragments and then use pins and plates and things to pull together those fragmented areas. Epiphyseal fractures, the epiphyseal plate, right, the growth plate, is already a weaker area. It's not ossified, and so that can be the actual location of the fracture. And if that happens, if it's a clean one, it'll probably be fine, but you can affect the growth plate. So if you have an injury in a young child, one of the first questions you probably will want to ask the doctor is did that fracture in any way affect their growth plate? If it's anywhere along the diaphysis, we're fine, right? But if it's toward the end, toward the metaphysis or where the growth plate is, then there could be an issue with the future elongating of that bone, and there could be an asymmetry to the lengthening of the bones in the future. There is the Potts fracture. This is the bimalleolar fracture. This is going to be occurring at the ankle and is going to affect both the medial and lateral malleolus. Where's the malleolus? The bumps on each side of your ankle, right? And the lateral malleolus is contributed by the fibula, right? And the medial malleolus is contributed by the tibia. And then the Coles fracture is a break in the distal end of the radius. So now we're down by the wrist. Those are just different terms you'll hear. They're more, the distal end of the radius has a little piece on it that can break off. And you may hear about these different fractures. Here's a picture of them, some x-rays of these. So here we see the spiral fracture. I'll show this one to you. And you can kind of see, let me change colors. You can kind of see there's kind of a spiraling to that fracture. Displaced. These two bones may not just simply reconnect normally. If they were not reset, they could begin to connect and ossify naturally and leave that person with a really abnormal bone. Here we see a compression fracture in the vertebra. You can see that there's been a force down that has compressed that area. Green stick, if you look here where the arrow is, you'll see that there's a fracture on one side, but the other side is not broken all the way through, so it's only broken partially, an incomplete fracture. Comminuted, there's a bunch of fragments in there. Here the fracture is at the epiphyseal plate. Potts fracture affecting both of the malleoluses, and at the distal end of the wrist you have the Coles fracture. So just a couple of extra ones. The other ones I think you've heard of before. What happens as we get older? What are we worried about? What's the disease everyone's worried about with their bones? Osteoporosis, right? And this is going to be a loss in bone density, primarily of the spongy bone, right? This is the spongy bone that is losing a lot of its density. The compact bone around the outside will still have osteons and lamellae, but when you look at pictures of osteoporosis, they're going to show these cavernous spaces becoming more porous. That porous area with the cavernous spaces, that's the spongy bone that is kind of being eaten away by the osteoclasts. So what happens over time, we can slow this down a little bit, but decreased nutrients, decreased osteoblast activity due to decreased nutrients, even less sun. Right? Because we don't get vitamin D. Vitamin D is an important molecule for the absorption of calcium. So right now, most of us are vitamin D deficient, which means that our digestive system cannot properly absorb calcium into our gut. So we could all be a little bit calcium deficient right now because of the sunlight, the lack of sunlight and UV radiation on our skin. Osteoclasts start getting a little bit more active. But again, it's mostly dealing with the spongy bone because that's the most metabolically active. Think about it. Compact bone around the outside. You've got osteocytes living in lacunae. Those cells are in semi-retirement. They're not doing a whole lot. They're not metabolically superpowers. So most of the activity, the metabolism of bone is happening within the spongy bone. And this is where you start getting some of these pathological fractures. A pathological fracture is simply a fracture that occurs because there was already an underlying disease. So when grandma falls and breaks a hip, she probably wouldn't have broken that hip if she didn't already have osteoporosis, right? So we would call it a pathological fracture. There was some underlying pathology that contributed in some large part to that fracture. Or a person, slips on the ice and puts their hand out and they break their wrist. If they were 30, it probably wouldn't have happened. But at 60, we start seeing more of these fractures because there are some osteoporotic changes to the bones. We've already mentioned that over time we get a little bit shorter. Okay, a part of that is the kyphosis that occurs. There is a curvature of the thoracic vertebra that over time begins to happen. This does not happen overnight, right? These are slow, gradual changes that occur to the overall skeleton. Every 5 years or so, you're an all-new skeleton, right? About 20% of your bones are being replaced, if you will, on average every year. So about every 5 years, you're a brand new skeleton, and these changes of bone loss, of kyphosis, are a gradual change. And also, because of a loss of mobility, right? Because with age, we're not quite as active, and with that can also come changes to respiration and more pneumonia and more blood clot issues. Again, all that thromboses and the blood clots can all be really contributed in some part back to the skeletal system and calcium regulation. Estrogen, a big one, right? Some of you ladies are dealing maybe with questions with your doctor. Should I or shouldn't I, or should mom or grandma, should they be dealing with estrogen replacements? At puberty, estrogen goes skyrocketing, right? And stays high all the way through until menopause. And at that point, the ovaries kind of start shutting down and the estrogen levels drop. And estrogen is important for bone health. And so women were taking estrogen supplements to minimize osteoporosis. What's the trade-off? What do we know now? What's the negative part to taking estrogen supplements? Anybody know? Breast cancer. A lot of breast cancers are activated. They're not caused by estrogen, but if there is a breast tumor, many breast tumors are invigorated, if you will, by estrogen. So by taking the estrogen supplements, if a woman has breast cancer, it can be a more ravaging kind of a version of that cancer. Okay? So estrogen is like candy for breast cancer sometimes. So if there's already a history of breast tumors, the last thing you probably want to do is take the chance of estrogen supplements. But that means you have to maintain your activity and your exercises and watch your calcium intake and do everything you can to minimize that bone loss. It just does occur, right? We're all going to face some bone loss, but it is more rapid in women. Now, men also have estrogen, right? We talked about how these, quote, sex hormones are not specific to one sex or the other. Women have testosterone from the adrenal glands, and so too men have estrogen. And that estrogen is formed also by the adrenals and a little bit even in the testes. Osteoporosis can also be an issue with young female athletes because they have a lower body fat. Lower body fat leads them to be amenstrual, right? They're not going to menstruate. Without menstruation, they're not going to have those estrogen levels rotating. So a woman who is not menstruating because of low fat levels or whatever other reason, again, the estrogen levels are lower, and that can lead to some bony changes, not good ones. So what do? We do ERT. We do estrogen replacement therapy. Again, that slows down the breakdown of bone over time. But again, as we've said, it does increase the risks of breast cancer. I don't like the framing of that. Not the risk of it, right? If you're going to get the cancer, it's not changing your risk. But if you are already prone to breast cancer, then those cells, those tumor cells, just eat up estrogen. They love it. But it also makes women more prone to stroke and heart attack. And that's exactly what we're learning about with testosterone, right? You're listening to the commercials. Some lawyer in Texas, if you took a testosterone patch or rolled testosterone under your armpits, guys, and you had a blood clot or a heart disease as a result, or you know, whatever, call us, right? There might be some money. So we know that playing around with hormones is probably not the best idea. Fosamax, Actonel are drugs you'll hear about on the market that are designed to slow down the activity of osteoclasts. So if we can't stop all of this, but we can slow it down. So we can slow down osteoclast and slow down the bone resorption. And there's even sometimes some parathyroid hormone can be given. It has to be given often. It's a daily injection kind of thing. There's no long-lasting patch or something that can be given for this. And that can also not only slow it down, but even increase bone density a little bit. So if you've got some osteoporotic changes, there are some newer technologies out there that can maybe start reversing some of this. But the best thing is not to go there at all. And to build up the best bone you can during those years where you are still actively building bone. So between 25 and 40, when you're in that height of life, make sure your bones are as healthy as possible so that when that decline does begin to happen, there's a longer hill, right? Longer decline. So make sure your bones are as healthy as possible. So you're looking here, this is spongy bone, right? This is that trabecula, the spongy bone. And you start to see the trabeculae here are kind of small, and here they're bigger. It's just you see that there's an increase in the, quote, porosity, in the pore size of the spongy bone. Okay? Let's talk. Is there anything at all about hormones? Anything at all about hormones? Any question at all? Let's take 5 minutes. We got 5 minutes. And flip back through, or anything about the autonomic nervous system that you're concerned about. Let's take 5-6 minutes to answer questions and just take a moment to review. I told you I'm not going to have a short answer question on the test. So you're not worried about being prepared to write out something in short in longhand. Yes?
Anything to, like, draw?
Nothing to draw, nothing to write out. I'm not going to go there and say, like I said, the questions I would have asked you are write 5 differences or compare and contrast the autonomic with the endocrine system. And rather than having you write it out in longhand and I read it in longhand, I'll use the Venn diagram kind of idea to quiz you on those ideas. Okay? I'll do that both for the question that would have been about endocrine versus autonomic, as well as parasympathetic versus sympathetic. Those would have been my 2 short answer questions. Compare and contrast, or tell me about the differences in these things. Yes?
In your packet, you have the, under other endocrine glands?
Yes.
The thymus and the reproductive?
Okay, thymus. I did not talk about the thymus. You can cross off thymus. Reproductive, testosterone and estrogen. Okay, just think about that. Was that somewhere else on the form?
It's just
On the backside under other, right? So what happens? So let's think about this for a second. Let's just do a quick review of this. Let's do the big picture idea here for a moment, okay? I'm in the brain. Hypothalamus. Hypothalamus releases a bunch of hormones, and all those hormones have what in their name? An R or an I. They all have releasing or inhibiting in their name, right? There's a whole host of them. And those hormones are named like gonadotropin releasing hormone, GnRH, or gonadotropin inhibiting hormone, right? And these hormones go where? These hormones travel just a short distance to the pituitary gland, right? And now there's a posterior and an anterior pituitary. Most of those hormones flow through a series of blood vessels, capillaries, called the portal system, directly from the hypothalamus down to the anterior pituitary. And what would those hormones do? Either encourage the release of or inhibit the release of 7 different hormones that come from the anterior pituitary. Now, before I get there, what else does the hypothalamus make besides releasing and inhibiting hormones? Oxytocin, I heard a whisper. Oxytocin and ADH. Those 2 hormones are made by the hypothalamus. They're released by really funky neurons that go right from the hypothalamus down to the posterior pituitary. And these 2 hormones, OT and ADH, are stored in the posterior pituitary. They're not made there. They're simply stored there. So that's the hypothalamus. Anterior pituitary makes 7 hormones. Let's see how many of them you can name off the top of your head. Growth hormone, ACTH, TSH, LH, FSH, prolactin, and melanocyte stimulating hormone. That melanocyte stimulating hormone is only during development. Never really talk about it again. It's going to help make your melanocytes, right? Make your skin pigment. So we'll kind of take that one off the picture because it's really not that important. These other 6 are going to go to different places. Where is the growth hormone going to go? Kind of general. It's going to talk to your bones. It's going to talk to your muscles. It's going to talk to your general growth, okay? Kind of a general hormone. ACTH is going to go where? The cortex of the adrenal gland, right? So we know it's going to go, there's the adrenal gland, there's my kidney underneath it, and it's going to go to the cortex, to the outer layer, right, of the adrenal gland. TSH is going to go where? Thyroid gland. Luteinizing and follicle stimulating hormone are going to go to the, that's an ovary, okay? And, right? And to the testes. If I can do any better there. How's that? I don't know, right? Whatever. Okay? It's going to go to the ovaries and the testes. Where is PRL going to go? It goes to the mammary glands. It also speaks to the testes. It also does speak to the ovaries and is involved with egg and sperm production, okay? So it's going to go to the oh, how do I do this? Oh, this is going to be awful, right? Okay, it's going to go to the mammary glands. And my artistic skills are horrible, right? So it's going to the mammary glands, and it's going to also speak to the gonads, okay? Now, let's talk about once ACTH goes down to the adrenal cortex. Remember the adrenal cortex? It's in 3 layers. The adrenal cortex is in 3 layers. The outer layer is the glomerulosa. The middle layer is the fasciculata. And the inside layer is the reticularis. Okay? And I told you there was a specific hormone from each of those layers I wanted you to know. I said the words salt, sugar, sex. In that order. Salt, sugar, sex. When you hear salt, what hormone's involved with regulating your salt? That ends in -one. Aldosterone, right? So aldosterone is the major mineral corticoid. From the middle layer, glucose, the glucocorticoid that I told you to know by name was cortisol. Cortisone, cortisol. And from the reticularis, sex hormones. That's where women are making testosterone and guys are making estrogen, right? It's from that area. And then where do those hormones go? They go to different places, right? Think about that. From the thyroid stimulating hormone, it goes to the thyroid gland and does what? Tells the thyroid to make thyroid hormone, right? And thyroid hormone comes in T3, T4, 2 flavors. Luteinizing hormone and FSH go to the gonads. They would be called gonadotropins because they're going to influence the gonads, right? And FSH and LH are going to affect the levels of testosterone and estrogen. We'll get to more of that when we get to reproductive. We'll get to a lot more of this. We'll get to touch on a lot of these hormones at a different time as we get there. Right now, we're just trying to piece together the big picture. That's a big picture review, isn't it? Did that seem comfortable? Or did that seem horribly, horribly like, I don't know what I'm talking about. What are you talking about? Hopefully, at least you're moving that direction. Now, how do all these hormones work? They all feed back by what's called negative feedback. So, if you had too much thyroid hormone, and what do we need to make a thyroid hormone? We need some iodine, right? But if you had too much thyroid hormone, you would tell your thyroid, cool it, right? And you would go back and negatively feed back there. And you would even go all the way back to your anterior pituitary and say, you know what, cool it. We don't need any of that TSH stuff right now either. So there's a lot of this negative feedback regulating these hormones. Now, what I did not talk about here, right, that's just the anterior pituitary. I didn't go to the pancreas and talk about alpha cells making glucagon, beta cells making insulin, D cells, and F cells. I didn't go to the adrenal medulla and talk about how it makes catecholamines, epinephrine and norepinephrine, and dopamine. I didn't go to, that's it? That it? Those are the big ones, right? Did you notice I did that at the top of my head? You should be able to do that too, right? You really should be able to go to a whiteboard, and this is not a lot of detail. I mean, it's a lot of stuff, but it's not horrifying, right? And you should be able to kind of go to a whiteboard or to a piece of paper and kind of sketch out the same idea. You really should be able to do that walking into the test. I won't ask you to do it on the exam, but you need to know these overall stories. And then ask yourself, you know what? If I didn't have this particular hormone, what might the effects be? Okay? I will see you all on Thursday.